Now it's okay. Which screen visible? My screen is visible.
Yes, sir.
Okay. So in today's class, we will see how to map the world using ROS, how to do navigation. But first, we will do the mapping, and then we do the navigation, autonomous navigation, collision-free navigation in the simulation. And later, we will integrate the ROS in the hardware platform. So for that, we have the Arduino Raspberry Pi, and also we can see how to communicate between the microcontroller and the laptop, and how to communicate using SSH also. And in the last, we discussed about the object detection using ROS and YOLO. Okay. So for the navigation, we just need a map in order to send the commands for robot to move that environment. Okay. So here you can see that there's a picture of a map. Okay. And you can see that there are some white spaces and the black spaces. So how it will make the map? It will calculate the threshold of that particular area or the grid. So what it will do, what the robot do, it breaks the environment into the grids, and then it calculates the value of the threshold. So if there's any object there, it indicates with the black line, and if there's no object or the free space, so it appears as a white space. And then we can save the map in our local folder. So it will store the map in some formats like PNG, JPG, or PGM. We can also visualize after we save the map. Okay. And also side by side also save the configuration file, which save in a format .yaml file. Here you can see the some parameter of the map. So it will store some information of the map, such as the name of the file and what are the resolution the robot have that particular map, and what is the starting point of the robot means origin, and it also tell the threshold value. So suppose if the value is greater than 0.65, it appears as dark, and if the value is lower than uh, yes, the cell yes, and if the value is 19 low than less than 19.6, it indicates that there's a object, and then it appears as a black line. So in this way, it will map the environment. So once we have the map of the particular environment, then we can do the path planning. Okay. So for that, you just need launch that particular command. So here we can use any robot. We can also use our custom robot for the navigation, for the mapping also. But it's better if we use the some predefined models of the robot. So Turtlebot 3 is a very useful robot used in the academia and also in the research lab. So we are using the Turtlebot 3 for the mapping, and then we do navigation on the same robot. Okay. So first we have to launch the file. So there are many methods or to generate a map. The traditional method which was followed in the previously, what they do, they just make a map by manually and then they train the robot in the particular environment. But now there's a method which is called SLAM I was now introduced, which is simultaneous localization. What is it? So we can do mapping with a SLAM, which is simultaneous localization and mapping. What the robot do, it navigate in the environment and also it localizes particular its origin location and then also mapping. So side by side, it will do two main things. It takes the information of the robot localization and also it do the mapping. So there are many methods for the SLAM also, such as G mapping, core SLAM, graph SLAM, and hector SLAM. Also now we have the very good for computational power, so we can also do SLAM using the camera, which is called visual SLAM. But the problem is that visual SLAM takes so much computational power because it generates a map using the depth particle filter information. So for this lecture or for this class, we will use a G mapping, which is a very, I think, low computational method. Or it takes the information from the laser scanner and generate a map. Okay. So now we have the robot. So both of you have these Titlebot 3 files. So it's better you can also run simultaneously. Dr. Shiva and Mohammad Ali, you have the file for Titlebot 3.
No, sir, I was not able to do this, but I'm watching it and I will do by myself next time.
Last time you said you didn't have the cat ROS in your system.
Yes, I have installed ROS, all the things, but due to my practical exams, I was not able to cover the last 3 lectures.
So currently you have the ROS installed in your system or not?
Yes, sir, I have ROS installed in my system, but I haven't entered it bot.
So just import the file from the GitHub because better you can run now. So you can better understand the things.
Okay, sir.
You just need these packages. Let me share the link with you. And what about Mr. Shiva, Dr. Shiva? You have the file?
I don't know this file. I don't know.
You also don't have.
Uh,
Okay, then both of you just import this particular package from the GitHub, Turtlebot simulation, and all the necessary files.
okay.
So you need this one, this simulation package, Turtlebot 3 simulation package. One is the Turtlebot 3 messages package, and that application package, and application message package. So clone these 4 packages and then source of folder.
Will you share that link, sir?
What?
Will you share that links?
Yeah, okay.
Jitter links.
Okay. Done.
Yes, sir.
Okay. So once you source it, you just run this. You run this line, and then it will open this window. So now we will do the mapping of this particular environment using the help of G mapping, which is a SLAM-based technique. So when you start the Gmapping file, it will open the ROS tool where you can visualize the mapping information. So here you can see that there are some green lines and the black line. So basically the black line indicates the global map and the green line indicates the local map. So what's the difference between the global map and the local mapping? So the global map rely on the global planner where you have the two information only and it indicates only the optimal solution. Suppose you give the start point and the end point, it gives you the optimal solution to reach towards the goal. But in the local planner, you have the information coming from the sensor. So for that, we have only one sensor, which is a laser sensor. So here you can see that the green line indicate the sensor value. So this is information coming from the local map, and the black one, which is the global map. Okay, so if we discuss the difference, what is that? The local mapping depends on the sensor base, and the global map depends on the map base. So basically, you give the map to the robot, so it will first do the global part, and the global part send the information to the local planner. The local planner gets the information from the sensor, and then it gives the command to the to the velocity command, so that to move the robot from the A point to B point. And it's the reactive navigation means a very short-term planning, and the global map is the long-term planning. And the local planning is always done on the online. What does it mean? That we have the cost map. So for the global planning, we just turn off the cost map, and for the local planning, we turn on the cost map. So in order to move, we have to run the tally of command. So here you can see when I move the robot, it generates the global map. Okay. Okay, so now we have generated a map of our environment. Now we have to save that environment in the local file. So for that, you have to just run the map server node. So, now what is map server map server? Okay. It's not the ROS one. Oh, okay. So you can see we save the file in the map folder. So this is the PGM file, and that is the configuration file. This is the path and the resolution, and then the origin from where it starts, and then there's a threshold value. Okay. So now we have a map. So how to navigate in that particular environment. So for that, in the ROS, we have the navigation stack, which is provided by the ROS. It's a very helpful package, which includes all the main packages for the navigation. So here you can see that we have the package of the localization, which is AMCL, Adaptive Monte Carlo Localization, which have the information about the sensor transform and the audiometry source. So this package is used for the localization. This is the package for the map server. It takes the map server information, which we already now stored in the configuration file. So it takes the configuration file, and then it gives the information to the global cross map. So you can see we have the two map, which is global and one is local. Okay. And also we have the sensor information coming from the laser sensor. And then we just give, once we have all the information, we give information to the robot in order to move the robot from starting to endpoint. So this navigation stack can be used in any robot. It is not necessary you use in particular robots. You can also include that navigation stack in your own robot, custom robot. You just only include that navigation stack and that particular file in your URDF or in your package. Okay. So this is the description of the packages. The map servers, which offers a map data as a raw service. It which what it do, it just takes the information which we stored in the configuration file, which is that particular file. So it takes that particular particular file, and then all the information it takes, and then generate a map. Okay. Then we have the G mapping. Already built a map using the method called G mapping, and then we have the AMCL package for the localization, because the main problem for the navigation is the localization. The robot has to know that the current position of the current position of the robot. So once we have the information, then it's able to navigate from one point to second point. Then we have the global planner and the local planner. I already discussed that the global has the information of the whole environment, and the local has only the short-term planning or the short-term knowledge, which coming from the sensor. And once we have all the information, it get information to the move base. So that particular node is very useful node. If we don't have the move base node, we cannot able to navigate. Okay, because it links together the global planner and the local planner. And this is the flow chart, how it moves. So first we have to describe the goal where the robot has to move. Once we have the goal information, it gives the information to AMCL, which is a localization package. Once the robot has the current position knowledge, it generates a path planning. So there are many methods for the path planning also. So first we have to describe that one. So there are three main type of path planning classification, which is classified as based on environment, based on algorithm, and based on completeness. So we have two types of environment. One is static environment and one is dynamic environment. In static, we have all the objects which are not moving. We have no moving object. So in navigation in static environment is far easier as compared to dynamic environment, because we in dynamic environment we don't know the location, we don't know the information about the moving objects, because once we create a map, it only gets the information of the static object, not the dynamic. So in dynamic environment, navigation is a very big challenge. And then we have the navigation on the based on the algorithm, which is local and global. So in the G mapping, we just do the navigation using the global and local planning. And also we have the path planning using the based on completeness. So here we have the exact and the heuristic. In exact, we have the optimal solution of the navigation. Means we already described how the robot move from one point to another. But in heuristic, we have multiple options, and then it choose the shortest path to reach towards the goal. So once the robot plan the path, it send the information to the move base, which links the global and the global planner and the local planner, and then it gives the information to the odometry or the CMD velocity. Okay, and then information goes to the base controller. So in this way, the whole navigation process done. So as I said, we can include the navigation stack in any robot which has the differential rev or the holonomical robots only. And also you can generate the uh, laser information from the Kinect also, because Kinect has the lasers sensor inside the Kinect box. Okay, so you can also do navigation using the Kinect. So in the global planner, we have the navigation function package, which provides a fast interpolating navigation function that creates a plan for the mobile base. So how it generates the information using the method called Dijkstra algorithm. So Dijkstra algorithm is a very useful algorithm. What it do, it just generate a multiple path, and then it choose only the shortest path to move from one point to from A point to B point. So if you want to know about more, you can search on the YouTube. We have many tutorials on the Dijkstra algorithm. So you can find it. Basically, if we have the nodes and the vertices, and then it calculates the shorter distance between one node to second node. Okay. And for the local planet, it's used two different algorithms. It's called trajectory rollout and a dynamic window algorithm. So what we have once the robot once you set the goal location, there are multiple paths to reach towards the goal. So first at the starting, it generates a multiple path, and then as the robot moves from one point to second point, it changes the path and then only choose the optimal or the shortest path reach towards the goal. And for that, it used two algorithms. It's called trajectory rollout and the dynamic window algorithm. And this is the step followed by the local planner. First, it discretely sample the robot control space. As I told you, that it moves in random direction. We have the velocity commands x and y, and then the angle command. Okay. Then it evaluate each trajectory resulting from the forward simulation using a metric that yeah, as I told you, that it only choose the optimal part and it discard the illegal trajectory. Means it discard all the trajectory which are not useful, to save the time and to save the memory. Okay, and then it pick the highest scoring trajectory and send the velocity to the mobile base. So for localization, it uses the package called AMCL, which is Adaptive Multiple Localization. It is a probabilistic localization system. So what it do? It uses the particle filter information coming from the laser sensor. Okay, and then using the odometry information, it calculates the particle information in order to localize the current location of the robot. Okay. So for that, we have the subscribe topic, which is scanning coming laser sensor coming from the laser sensor, and then it published the robot to the particle plot and MCL post. So now we have the navigation map file. So now we are running that line. Any question regarding the navigation until now?
So local cost map is the map that we have created using a local planner, isn't it? Global planner.
Your voice is not clear. Shiva.
So actually, what is
Okay.
meant by local cost map, sir? Actually, the map that is created from a global planner, is it?
So basically, local cost map and the global cost map contains information about the map. Okay, the map we already
Okay.
built. Okay, so
Okay.
that cost map send the information to the local cost map. Okay, local
Okay.
cost map takes the information from the sensor, and that information goes to the move base package. So the
Okay.
move base, what the move base do, it combines the local cost map with the global cost map, link the information, both the information. Okay, and that information goes to the odometry file or odometry package and the CMD velocity topic. Okay, to move it. So the global cost map contains the information of the long term. Means it contains all the information about the map. But the local cost map contains the information of the short term. Means only the few information about the map.
Okay, sir.
So if you open the launch file of the navigation file, so here you can see that first it will take the node from the map server. So the map server, what it will do, it gets the information from the map file. So here you can see once we generate a map, it is does not cover that particular environment, particular area of the environment. Okay. So if I open the RV, you can see that information is also missing during the navigation. So you can see that it only show the information which already shown by the robot. Okay. So it first generate the map server, then it start the AMCL file, which is the localization file, and then the move base file and the ROS for the visualization. Okay. So here you can see we have the black line, which indicates the global map. And also you can see that the small rectangular bar, which is the local map. So here you can see the difference between the local and the global. So the global map contains all the information about the map, and the global planning contains the less information about the map. So this green line again shows the sensor values, and also that particular the blue area indicates the local cost map. And here you can see that the multiple arrows around the report, which is indicates the localization or the trajectory. You can see the trajectory of the robot. So there are multiple paths already shown by the robot. So once we move the robot, you can see that arrows become shorter and shorter. So it will take only the optimal solution to reach towards the goal. Okay. So first, what we have to do, we have to assign the current location of the robot. Okay.
So which one is local map, sir? Here?
Local map is that particular area, that's small rectangular box. This is the local map. And the big one picture shows the global map. Here you can also see that in the RBIS, we have the global map. You can see when I turn it, the particular blue area gone. So that is the global map. And for the local map, this is the local map, the blue area.
Okay, sir.
So first we have to. So currently our robot is near the table. In the RBIS, you have to. You have to set the current location using this tool, which is called 2D estimate. So when I click it, it will come, the robot comes here. So for the goal point or the ending point, you have to just click the 2D navigation goal and then run it. So here you can see that optimal the robot choose a particular path to move towards the goal. But when it comes to that particular area, it again change the path. And also, if you can visualize the arrows are now shortened.
So how will you give this goal position, sir, for this robot?
There are two ways. Either you give the information using the topic, goal topic, or you just select this 2D navigation goal and then click it.
Okay.
So here you can see when I click that particular area, it does not choose the optimal path because that particular area of the environment is not shown by the robot. That's why it takes the wrong path. So when it reaches that particular area, it again confused where to go. And then once it confused, it moves around and around. Here you can also notice that. So now there's no path to move towards here. So now it stop. Now it will rotate in the same direction. You can see.
Yes.
So further you have to change the again every goal path. Okay. Also here at the configuration file, you can change the parameter of the move disk, of the global map and the cost map. You can change that information from here. If you want to reconfigure the localization parameter, you can change from here. How many particle, minimum particle, maximum particle you want it. Okay. So any question regarding this?
No, sir.
So this is one way for the autonomous navigation using the SLAM base. You can also do navigation using the machine learning tool, and you can apply the deep learning methods like reinforcement learning method. When the reinforcement learning, you don't need the information about the map. What you have to do is just train the robot in the simulation environment. Okay, and then it learns the robot learn from itself. So this is the one way for the navigation also. The other way is you can use the supervised learning. You just take the multiple images uh, of the action and then classify the action accordingly uh, for the images. Okay.
Reinforcement learning, how it will get the path, sir? So without giving map.
In reinforcement learning,
How it will the robot will get path. Um, so here in reinforcement learning, we don't give a map, sir. So without
so there are two
having map,
ways. To train a robot using reinforcement learning. The first one is the without path planning. You do not give the information about the goal point. Okay, you just give the environment, and the robot move from its own action. Okay, and then it chooses only the optimal solution of that particular area. The second one is you give the starting point and the ending point, and you force the robot to move from point A to point B only. There's no other point. So in my masters, I developed a novel method for the reinforcement learning method. Okay, but that one I did not incorporate the path planning. I only incorporate the autonomous navigation. So what the robot moves in a random direction, and the main aim or the goal of my method is to just avoid the obstacle, the static obstacle and the dynamic obstacle. So we can train using the many methods using RRT. You just uh, give the information about the starting and the ending point, and the robot always choose that particular path.
Okay, sir.
Any question, Mohammed Ali?
So in reinforcement learning, how we will define constraints like boundaries, etc. All the things.
What you mean by constraint means?
So, for example, the meaning of reinforcement learning is if the robot is doing something good, so we should give something bonus, etc. This type of thing. So how we will be implementing this in this?
Okay. So if you want to train a robot using reinforcement learning, so there in reinforcement learning, there are two main things. One is the agent and one is the environment. Okay. So we have the environment. This is environment, and we have an agent of a robot. So the robot moves in the direction, and if he moves towards the goal, give the positive reward, and if goes against the goal, it gives the negative reward. Okay.
Okay, sir.
When I was doing my thesis project, I trained a robot for autonomous navigation. So for that, I just make a reward function. So if it goes towards the goal or towards avoids obstacle, it gets the positive reward, and if it hits the obstacle or the wall, it gets the negative reward. So it's a closed loop cycle. Okay, for the training. If you are interested to work on the reinforcement learning, I can help you.
Okay, sir. Sure.
So now the question regarding the navigation. So we can move forward.
I have doubt in previous classes. So joint state publisher and robo state publisher. So what is the difference between these two?
Join state and the robot state publisher.
Uh,
So the difference is that the join state contains information about the links. Means you have two joints and they have the links between them. So it only stored the particular information in the joint state. Okay. But then the robot state, you have all the information about the TF. Means you have the sensors, you have the wheels, everything. Okay. So it contains
okay.
all the information about the whole robot.
Okay. So, in ROS control itself, it will give information about joint velocity and information about the robot states. Is it so? In ROS control.
In the ROS control,
So,
we have the robot state information. Of course.
uh, robots information.
Yeah.
Okay. Okay. Sir.
So now we will run the ROS in the embedded boards. So there are multiple boards available or microcontrollers available in the market in which you can run the ROS. The basic one is the Arduino, which is easily available in the market. And you can communicate easily between the Arduino and with the laptop. So how to communicate with the Arduino? There's a serial library which is coming already published or proposed by the ROS. You have to import that, incorporate that ROS serial library in your laptop, And this way you can easily communicate between the Arduino and the laptop using ROS. Okay. So first you have to set all the particular packages for the ROS serial for the communication. For this, you have to run particular line. Here you can change the distro of the system. Suppose you have the melodic, then you have to change the melodic here. Or if you have the neotic, which is the current ROS version, you have to change it here. Okay. Also, if you don't able to download using this line, you can also, there are multiple packages available on the GitHub. You can just clone all the libraries in your workspace and then run the ROS serial library. So what it will do, it will make the communication between the microcontroller and the laptop. So it makes the Arduino node, and then you can just run the node. Okay, and also you just make the lab. You just download all the libraries of the ROS using this line. Okay, once you have the libraries and the ROS serial library in your workspace, you have to open the Arduino, and then you have to code it. So the main library for the communication you have to include the ROS.h. So this library links the microcontroller with your laptop or with the ROS. And then you have to, okay, if you don't, I think you already know how to code in the Arduino. So Arduino follows the C++ language. So you can see we have the two main loop, which is the setup and the loop function. Okay, and then we have to make another function which is called subscriber function. So once we write the code in the Arduino, we have to run it. So I just discuss how to code in the. So basically here I make a subscriber function in which the function of the controller is to open the light or the LED when the data is when the value of the data is greater than 1. So it opens the light, and if it's less than 1, it closes the light. Okay, this is the function of the subscriber. So for this, you have to include the ROS handle node. Here you can change, you can put any name. It is not necessary you could put NH here. You can put any name here. But this one is the constant. You have to start with the ROS and then node handle, and you can put any name here. Okay. Then you just make a function. Once the data is greater than 1, it opens the LED, and if it is less than 1, it closes the LED. Then you have to start with the subscriber, which is the with the name of the subscriber, which is LED toggle, and the function. So this is the function you already wrote it at the starting. Then you have the setup loop and the setup function and the loop function. So in the setup function, you just define the pin number, which is pin 9 output as the output, and then you have to initiate the node and then subscribe it. And in the loop function, you have to run again and again. So you have to spin, and then you have the delay of 1 millisecond. Okay. Once you write the code, then you have to run it here. Means you have to compile it or you have to burn it. Once you burn the code in the Arduino, then you have to allow your port in order to read or write it. So for that, you have to, once you connect the Arduino port, you will get the information here. So here you can see that my port is connected on the ACM 0. So you have to allow the controller to read or write here. So for that, you have to run this line, and then you have to run the node for the serial communication between the controller and the ROS. And then you have to assign the controller path. Okay. So now I'm connecting this Arduino with my laptop.
Sir, is there any way that we can burn the Python code in Arduino?
No. You can communicate with the Python, but you cannot burn the Python code in Arduino because Arduino follows the C++ language. You cannot burn it. You can write in Python for the subscriber and publisher for the communication. I will explain you how to write in the Python, also communicate with the Python and the Arduino.
Okay, sir.
Okay, one more thing. Where you always put all the Arduino code in that particular file folder where you have the ROS libraries. Otherwise, your code will not run. Okay. So these are all the packages for the communication between ROS and the microcontroller. So you can see all the libraries are here. And the main library is the ROS-H, which link with the ROS with the Arduino. Okay. So here you can see that my port is connected on the ACM0. So first, you choose the board and the port, and then run it. So you can see it indicates that there's no permission to upload the file in this particular port. So first, I have to give the permission. So now my port is uploaded in the controller. Now I have to connect using the ROS serial. So for that, I have to start. First, I have to start the ROS port. So here you can see that now it is serial connected with the Arduino board. And also we have one subscriber, which is named LED toggle. You can also visualize it using cross topic list. So we have the topic LED toggle. So if we get the information, so we have the subscriber serial node. We have no publisher. So if you want to publish the data, either you just make a code for the publisher using the Python or any language, or you can also give the publishing command using that line. So this is the topic name. This is the message file, and this is data. So currently we have on the state 0. So we make a file. If the data is greater than 1, it opens the LED number 9. So if I open my camera, okay. So we can see the LED now turn on. Okay. If I put 1 here, it will turn off. Okay. Also, you can make a Python file for the publishing. So for the communication between Python and ROS, you have to include the ROS file library. Then you have to include the message file, which is standard message.flow64. This is type of the message. And this is the for random generator and this stuff. So first we have to initiate the node, host.initiate node and the node. And then we have to make a publisher node, publisher topic using the line publisher. Where you have to publish, we have to publish on the same subscriber topic. So we have the subscriber topic name as LT toggle, and the message was flow64 and the queue size is 10. Then we have to start with the while loop. It will run it once we forcefully shut down the ROS. Okay. Then generate the random number between 0 to 2, and then it gets sent the information to the publisher, and then it will on. So if I run this publisher code, if I think this, so you can see I was connected with the mobile phone. It is not easily visualized. We can see how to communicate between the Python and the Arduino and the ROS. Okay. Any question regarding the communication?
So when we publish the command velocity, if you are using a mobile robot, when we publish command velocity, whether we can send the command velocity through this mode. So in the same way, we can send command velocity to the mobile robot.
Yes, you can
Is it
do the
possible, sir?
same.
Okay.
Yes. Yes.
Okay. So there is no apart from this possibility. Is there any other possible to send command velocity, or is there any possibility to interface hardware with ROS? Sir?
You
So
can
this is
make
the
a
only.
no. You can make a publisher topic using the Python. Means you just make a Python code, okay,
Okay.
where you get the information from the subscriber. Then you just move the robot in the in any direction. You have the three values. Means you have the velocity in the twist message. So in the twist message, you
Yes.
have the x position, y position, and the angular position, angle information. Okay. Then
Okay.
you have once you have three information, you have to publish on the CMD velocity command or topic. Sorry.
Okay.
Last time we just
Actually, we are
run
facing.
on the simulation. The
Ah,
same
yes, sir.
the same way.
Same way we.
The same way.
Okay.
I
We are
will.
doing like that, sir. But we are
Okay.
facing much difficulty when we are rotate the robot for particular angle. So we
So
need
you
to
have
control.
the robot and everything currently.
Yes, sir.
So we
Yes, sir.
can
We have.
discuss it.
Okay. Sir.
Okay. In the last we will discuss it.
Yes, sir.
Okay. So now I'm uploading another code. Okay, where I will run the four LEDs which are connected on pin 8, 9, 10, 11, and I will turn the LEDs on and off using the information from the hand. Means I will track the do hand tracking, and from the I will get the information from the hand, and then I will publish on that particular LEDs. So I use the same code as previously. If the message data is equals to 1, it will open the 8 LED. If it's equal to 2, it will open 9, and so on. Okay, so this is the same code. So first I have to close the communication between Arduino and the ROS, and then burn it. Once it's done uploading, you can again start the ROS serial node. Okay. Okay. So here I make a tally of file. You can also replace with the motors. Now I'm controlling the LEDs. You can control the motor using this node or this file. So if I press a W, it will blink one light. You can see that the green line turn on. Okay. And if I put S, it will open the red light. If I press D, it will open different light and a different light. So now I'm controlling the LEDs using the keyboard. So you can replace the LED with the motors in order to move the robot. Okay. So in this way, you can control the motors. Okay. I also control the LEDs using the hand motion. Here you can see I make a code where it detects the location of the hand of the fingers, and then by using that information, I turn on the LEDs on and off. Currently, I will not able to run this code because in Zoom my camera already running, so I cannot run that code. So you can do multiple things with the controller and communicate with the ROS easily. First, we have to write the subscriber node or the publisher node in the Arduino, and then we have to write another code in the Python to communicate between them. Okay. So any questions so far?
No, clear.
So Shiva, you can control the motors like this.
Yes, sir. Okay. Now I understood.
Okay.
Actually, we have a problem in rotating the bot for particular angle. So we need to rotate the bot for 90 degree.
Okay.
But if we give more than 10 degree tolerance, it will turns. But
Your
it will
I
not be useful for
your
attaining our
IM
task.
IM is calibrated or not? Means calibrate the IM.
No, sir. We are calculating that angle using Arco markers, using vision system camera.
Oh, camera. No,
Actually,
it's
the
okay.
problem
But with
statement
the
is like,
with the motor, you have to incorporate the IMU. How you know the information?
yes, sir.
How you get the information from the motor? From which sensor?
So in bot, we didn't include any sensors. That is a problem statement they have given. So we are not able to include any sensor in the robot. In the problem statement they have given. So don't include any sensor in mobile robot. So we need to follow the centralized system, that is camera. So with the camera, we need to get all the odometry data of mobile robots.
Hmm.
So there is a problem statement they have given in Flipkart challenge.
Okay.
So if we place IMU sensor, is it possible to rotate the bot for particular angles? Will it give
Yes.
more accuracy?
Yes. Because with the
Okay.
IMU, we have the information about the odometry, means X, Y, and the current location of the robot. Okay. With that mind, you just easily calculate the angle
Okay, sir.
accordingly and then send the command to the robot.
Okay. So we will try to add this.
With the motors, if you are using a simple DC motor, you can just add a laser sensor or the encoder between the disc.
Encoder we have, sir, but
So with the
we are not
encoder,
measuring.
you get the information about the current motor location information. So you can easily
Okay.
give the commands.
Okay. Actually, the motor location we have got more accurate from vision systems, but angle is we are getting less accuracy when we are getting angle. So the
Okay,
angle is the problem.
you will show me. I was just ending the class in. So now
Okay.
we have seen how to run the code in the Arduino and to communicate with the ROS. Now we can install the ROS in the Raspberry Pi because it is not feasible to put the whole laptop on the robot. So what we do, we just run the ROS on the microcontroller, which is the Raspberry Pi. And these are the specification of the Raspberry Pi 3. It has a GPU and GPU, all the HDMI port. So we can see it's a simple CPU you can put on the robot. Okay. So most of the mobile robots use that particular controller, Raspberry Pi 3. You can use any other controller also, just like Jetson Nano, Udo. Okay. So first, what we have to do is just burn the Ubuntu image on the micro SD and then turn it on. So now I'm turning the Raspberry Pi. So now I'm connecting the Arduino with the Pi. Okay. So you have two options. Either you connect the Raspberry Pi with the HDMI, and then you see the visualization on the computer or the monitor, or either you just communicate with the SSH, which is a serial communication.